Hello, my name is Newell Kitchen. I'm a soil scientist with the Cropping Systems and Water Quality Research Unit. My co-author Ken Seth is an agricultural engineer in the same unit, and the title of my presentation is Geophysical Methods Needed in Agriculture. Where in the Midwest has the negative impact of modern agriculture been the greatest? Well, it's no surprise that right here in Columbia, Missouri, where we are located, is the first erosion plot research in the U.S., established about 100 years ago. This area of the country and the soils on the landscape are very vulnerable to erosion, and early settlers saw that this was a problem. And so when agricultural research started, this is one of the areas that was focused on. As a result of that, early settlement and tillage, cultivation of agricultural soils, we saw tremendous soil degradation. I like this slide because it kind of shows the cascading degradation from degraded structure and aggregation, compaction. You get the water erosion, reduced plant growth, poor soil biology, and eventually it just really eats away at the potential for growing crops on these soils and reduce sustainability. So there's need for spatial data in part because of the degradation that has taken place on these soils. And as we look across the landscape and look at how crop management exists today, and to also understand the environmental protection, we need a better assessment of that soil resource as it exists within the landscape. We do have some information. Historically, we've used in the past just soil maps as created by NRCS, but the resolution of this is often inadequate. We know that this degradation tremendous yield variability or continues to create a signature on the landscape of varying production. And this is about a 36 hectare field in the area where we do our research near Centralia, Missouri. 11 years of crop yield maps, and you can see that the variability within any year within the field is on an order of magnitude of at least 2, oftentimes 4 or 5 or 6 times variation within the field for a year. And some years they look a lot the same, and other years they kind of flop. You can take a quick peek at those and see that trend kind of flips back and forth, and that has a lot to do with the type of weather year that we have. So there's this tremendous variability there, and we see that you take those yield maps and you essentially turn them into profitability maps based upon prices of the crop, your costs of your inputs, and you can see that there are areas over a 10-year period within that field that you actually don't make production. Any area here that's in brown on this map is actually a loss of money averaged over those 10 years. And so understanding that spatial variability is very, very important. We have kind of boiled down our understanding of soil landscape factors that affect water and crop growth into 3 things. One being the plant available water storage, which is typically a function of the soil texture and organic matter. The rate of water infiltration and recharge, which will be a function of factors such as soil water porosity, layers impermeability, and slope. And then water redistribution within the field, where relative elevation, curvature, and slope are factors that kind of help drive that. So there's some things we, really in principle can see are going to make a difference and help define the site-specific nature of a soil and its ability to take in water, store it, and make it available for plant growth. Because year in and year out, that is still the factor that's going to affect plant. So that introduces the concept of sensors, and Adamchuk put this slide together kind of demonstrating to more of a general audience the different types of sensing you want to have and consider at least. And then taking these 6 different types of sensors, built this chart that kind of helps to illustrate some of those things that we have available currently or in development. So you can see, I'm not going to go into the details of this chart, but it certainly shows there's a number of different instruments being used specifically for agricultural production. and having a better handle on what they can do. And you can see here on the bottom row, it's the soil properties, chemical and physical properties that are generally targeted with these different classes or types of soil sensors. Much of our work in Missouri, we've tried a number of these different things, but we have found the soil electrical conductivity to be um, one that has been especially helpful in being able to measure and map variability and be able to relate that variability to aspects of crop and soil management. There are a number of different soil electrical conductivity sensors that we've used over the years, and have found many of them give us the type of information that is once calibrated to some calibration points within fields, we can make the a similar type interpretation with these different sensor types. So here's that same 88-acre field that I had the yield maps on. Here's the Circle soils map as it exists to the general public. We, in the early 1990s, had NRCS do a higher level, what's called the Order 1 soil survey, and this is what the soil map looked like. So you can see there's more resolution, but you take soil EC and you get this kind of resolution in a two-color gradiated variation. You can see that there's tremendous detail that you can catch with the soil electrical conductivity that you can't using the more conventional techniques that have been used in the past. So now I'm going to take a few minutes and I'm going to talk a little bit about some examples of how soil EC have been used in crop and soil management decisions, highlighting some of those things that we feel like are important and that producers are wanting to target as a part of being able to manage these soils. First, I'm going to come back to this notion of the topsoil loss from erosion, and the story of erosion is still not well accepted. I think there's a certain amount of denial that takes place with some people, some farmers, and so the more we can illustrate and bring to their attention the impact that not just past but current erosion has on fields, I think it's a story that needs to continue to be told. For example, here a couple years ago, this was a field adjacent to some of our research fields, not one of our fields. It looks like a furrow irrigation, but indeed what happened here is a fairly significant 4-inch rainfall event took place within a short 12 hours approximately, and those furrows are actually the seedling furrows, and you can see the corn emerged, actually not emerged, germinated, and the radicle anchored into the soil, and you can see each of the rows, and then this is the coleoptile of the corn poking up and coming up out of the ground, and so you have the 2 inches of soil that were over the top of this row of seed essentially has been stripped right off as a result of this erosion, and that's the gulling you get. So there's approximately an inch of soil that has been eroded from this position in the landscape, and that soil is very valuable. The most valuable soil we have is our topsoil, and so that cannot be effectively or very economically moved back up onto the landscape. So it's helping us using soil electrical conductivity and other sensing methods to kind of get at this story is really important. Back to our field, our case study field. This is what it looks like today, and you can see the depth to the argillic horizon, which is a very significant factor in the profile, drives the hydrology, and it's really the thing that gives us the tremendous variation in soil electrical conductivity and allows us to be able to map this variation very nicely. So you can see that's how the field is today. Using some modeling and some areas that have not been in production, we have been able to develop this is a map of that same field as we predicted it was 120 years ago, with this final map being how much soil, the topsoil loss in centimeters that exist on that field. And averaged over the field, there's been 13 centimeters of loss over this 120 years, with some areas being pretty extreme, as much as 40 centimeters up in this area of the field where you have the dark brown that's really stripped off some of the best soil on that field. So this is an important way of being able to get this information into the hands. We can then take this topsoil depth, look at it from the standpoint of the actual yield variability, and actually put a value to that topsoil and help farmers to see what the value of that topsoil is. An important take-home message that farmers, conservationists, crop advisors need to continue to hear. We have taken soil EC, and after having done a number of different types of soils, have developed what we call a theoretical relationship of soil EC to productivity, crop productivity. On the low end of EC, you have a relative low productivity because you have sandier soils and you're not able to hold as much water. You get into this area of the middle part of this figure, and you have more optimal soil water, and that's where you kind of get your optimized production, and then it tails off as you get more clay, and that clay prevents storage of soil water and makes has less available plant available water as you get more and more clay. So you kind of get this kind of a relationship, and we've seen this relationship exist within the same field as well as over across many different fields. So now taking and looking at our list that we had before, and we of things that are important relative to soil landscape factors, you can then see that using soil EC, we're able to get really at some of the soil texture and layers of impermeability by virtue of the depth of impervious layers, soil layers, as well as then with high resolution GPS data, either through LiDAR or ground-based GPS systems. We're able then to get at the water redistribution within the field. And we feel like that actually with these two measurements alone that we're able to go a long ways in helping us to understand variability within fields, get those high-resolution maps that may be used as a part of management going forward. And in fact, one of the ways we've done that is we've taken soil EC, elevation, and slope, and we've done some unsupervised cluster analysis on that data sets and have come up with management zones or environmental response units. Here 2, here 4, and here 6 different response units based upon these 3 factors, which then it starts to get at a classification of the soils that gives us much more detail than what we would have with a soil map from NRCS. Another example of how soil texture is important in using EC to get that is with areas where there's tremendous variability in texture, like in the alluvial soils of the river bottoms. You'll often get a lot of sorting of fines to coarser texture materials within a field, and many of those same fields are also under irrigation, and so that then essentially the EC can be used to develop a potential plant available water holding number, and then used to do in some areas of the country they're actually using this as the basis for doing variable rate water irrigation on these fields. So that's one application of this. Another application would be to look at pest control of some type, and in this case this is a field where the relationship between nematodes and their density in the soil was basically a function of the soil texture. And so where EC gives us a good indication of the soil texture and the variation of that in the field, the darker red in this map basically is where the intensity of the nematodes is the greatest, and or actually it's the area where EC is higher, and so then we can, with those areas there's not as much treatment needed, where you do have a lower EC or a sandier soil where the nematodes are more apt to grow and develop and populations soar. That's where you need to go in and do a treatment for those nematodes to prevent crop injury. Another example is to look at how we might use different methods. In this case, I'm going to use soil EC again to account for soil nutrients. And typically when we're doing assessment of soil nutrients, we will do that by taking a soil probe, and we go out there and we poke it in the ground, and we come out and it goes down to about 6 to 8 inches, and we use that very shallow sample to assess what the nutrient availability will be for the crop. Well, in fact, we know that crops go much deeper than that, and crop roots do. And so, do those subsoil nutrients that might be there, should we be considering that as a part of fertilizer recommendations? And one of the things we've been able to do is to look at soil profile potassium, actually phosphorus too, in some areas. In this case, again, the claypan soils in the northeast portion of the state, a number of different sites where we have developed a relationship that shows that when you the deeper the BT horizon is, let me state this differently. Essentially, the amount of potassium increases as soon as you get to that BT horizon. So the closer that is to the surface, the more soil profile potassium you have. So here you have where you have a very minimum amount of topsoil, you can see the profile potassium is much higher. As you have a deep BT, basically the profile potassium is much less. So this is a bunch of values taken on one of our research fields. Well, so we take that information, we take the soil EC information and that relationship between EC and the depth to that clay pan, and we're able to essentially transform that into a map of profile potassium, and where some areas are going to have much more than others. And so it's combining these two relationships together to get this map of profile potassium. And what's even a little bit more interesting perhaps is actually to take this then to put this into an animated model to actually show where that potassium is in the profile, with the blue being shallower amounts of potassium and the red being a higher levels of potassium in the profile. So very neat way of starting to view soils as they really are, and that is as a continuum in 3 dimensions. And in the past, that's not how we've looked at soils. We've looked at it as a very flat kind of a relationship. So this is could not get to this were it not for some of the geophysical techniques like soil EC. And I'm looking at my clock and seeing that I've taken 17 minutes, and that was asked to do this within 10 to 20 minutes. So I think I'm going to end there with this slide showing again some variability down on a landscape. Conclude with the following statement that the geophysical techniques that are out there and or that are being developed really are important to help us to understand the physical and the chemical properties of soils in that continuum relationship. And the more that we can take those soils and map them that way, express them that way, it's going to give us an ability to better target our management, both in terms of labor and agrochemical inputs, so that there's greater efficiency of those within the landscape, that we're more careful about the more vulnerable areas within the landscape, so that we can minimize loss to the environment. Thanks for your attention.